Hello, this is Network Traffic Analysis, NPS CS4558. This lecture is on IP geolocation. I'm Professor Robert Beverly. IP geolocation. So hosts on IP networks must have IPv4 or IPv6 addresses. Typically, these addresses are unique and are tied to the network attachment point, i.e., they are a virtual location. The IP address of a host must correspond to the network to which it attaches. However, there is no required or even implied binding between an IP address and a physical location. Therefore, IP geolocation techniques seek to answer what seems like a fairly simple question. If I'm given a host with a particular IP address X, where in physical space does X reside? When we talk about physical location, it's important to keep in mind that we may be talking about locations at very different granularities. Often this depends on the type of problem that we're trying to solve using IP geolocation. As an example, our problem may require only continent-level granularity of geolocation. Or, if we wish to be more precise, we may wish to know which country the host resides in, which state, province, or region, or getting even more fine-grained, we may be interested in the exact zip code, for instance in the United States with zip codes, the street, or even the exact house where a particular IP address resides. At best, we might want to know exactly the latitude and longitude of a particular IP address. However, it's important to keep in mind that many IP geolocation techniques are most accurate at coarse granularities. We'll see in future lectures techniques to do more fine-grained IP geolocation. So why are we doing geolocation? One of the primary drivers behind many of the commercial reasons for doing IP geolocation are location-based services. For instance, advertising is a big one. It's often the case that advertisers wish to send targeted advertisements to users based on their location. For instance, if I'm in Seaside, my advertising company may wish to display advertisements for businesses that are physically in Seaside. Similarly, economic demographics are important to advertisers. The particular products that may be displayed to a user can be a function of where that user resides and what their economic or socioeconomic status actually is. Content is another big reason for IP geolocation. For instance, many websites have content available in multiple languages, or they may have news articles that are pertinent to certain areas. Therefore, a website may tailor the content that's actually displayed or the language that's actually displayed to a user based on where that user is accessing from. Access, of course, is a big part of geolocation. We call this geo-walls. For instance, Hulu, eBay, and BBC all implement geo-wall type technology. In the case of Hulu and BBC, these companies restrict the locations from which their video is available based on the IP geolocation of the user. eBay, similarly, has different rules on what products they may sell based on the country in which the user actually resides. Reputation is another reason for IP geolocation. For instance, different IP blocks may be in countries that are known to have different kinds of spamming behavior, or in different kinds of countries that have different criminal type behavior. Similarly, IP geolocation is used for authentication. If you think about your bank, banks often will do IP geolocation to determine where different users are attempting to access the bank from. If a particular bank detects that there's someone, say, in South America trying to access your account, and then someone in Africa trying to access your account, this may be a red flag that your account has been compromised in some way. Emergency services are another important reason for IP geolocation. We'll talk in a moment about efforts by the IETF to provide emergency service support for things like voice over IP 911. Security is the third big reason for IP geolocation. It's often the case that during an attack or after an attack, it's important to try to understand where the attacker physically was coming from, or even in some instances, where the target actually resides. Similarly, it may be important to determine the set of locations where a particular device has been. If we think about a mobile target, that mobile target may be moving through physical space, and it may be important for security or even criminal investigations to understand exactly where that target has been, and we'll use geolocation techniques to do that. It can be important to understand the impact of different natural disasters or even man-made impacts on the network. As an example of a large-scale network impact, we can think about things like the Arab Spring and instances where different countries, such as Egypt and Syria, completely turned off their entire network. In these cases, it's often important to try to identify the set of hosts and IP addresses that are in those particular countries, which have access, so on and so forth. We spoke previously about different kinds of geo-walls, authentication, and ways for trying to allow companies to understand where hosts are coming from and accessing the network. Similarly, geolocation from a security standpoint is often important to efforts to either provide censorship or to circumvent censorship. If we think about users in particular countries that are trying to access particular other websites, often their governments will imply controls to enforce country-based access rules. Similarly, with anonymous communication, geolocation plays an important role not only in routing the requests, but trying to circumvent different kinds of tracking mechanisms. So let's talk about when is IP geolocation actually required. And at first blush, when we talk about IP geolocation, this may seem a bit contrived. After all, hosts know their IP addresses and their location. If I pick up my mobile phone, this device has an IP address, it has a GPS receiver, and it certainly knows where it is. Even if I don't have GPS, it's often possible to do triangulation off of things like available Wi-Fi beacons. And there's companies that offer services for doing exactly this. For instance, Apple's IP geolocation for client phones is from a company called Skyhook. However, a host may not actually know its location. So for instance, I may not have GPS signal, there may be no Wi-Fi, or perhaps I'm indoors. Further, perhaps I simply have a desktop machine that has none of these different ways of doing geolocation. But more importantly, we may be a third party. So we may not be actually the host that we're trying to IP geolocate. So we're trying to geolocate a device other than our own. Even if a device does know its location, if we're a third party, it's probably unwilling to share its location with us unless we have a trusted relationship. As a particular example, let's think about a web server and a client accessing that web server. Frequently, the web server would like to know the location of the clients that are accessing it, and it may be part of its required policy. So the web server may only serve content to hosts that it believes are physically in the United States. How can it do this? Well, it's important to note that in modern web languages, such as HTML5, there are things like geolocation APIs that allow the web server to actually request the location information from the host. We have a picture of this in the lower right-hand screen, and you may have seen this when you've been browsing different websites, where the website will cause a little pop-up box to come up on your web browser that says, "This website wishes to know your location." This is all part of HTML5. But the client may not allow this location to be sent, or it may not know its own location in the first place, so it couldn't send an accurate location, or it may simply lie in some way. So again, consider this example of a web server that wishes to do IP geolocation. How can it do it without things like explicit support and explicit locations from a particular web client? As a second example, many students have probably taken the forensics class or are at least aware of forensics-based media research. So an example is, let's assume that we've recovered the hard drive from a criminal. This hard drive is going to contain all sorts of interesting information and metadata, things like documents, emails, so on and so forth, but it also contains other interesting metadata, such as IP addresses, or think about DHCP leases, the IP addresses that have been given to this machine over time. This can illuminate lots of interesting aspects of a particular criminal or terror organization. So for instance, when and where did the criminal connect to the internet? And with what remote servers was the criminal connecting? All of this sort of post facto, post-mortem analysis is extremely important. Below, I've presented a screen capture of a tool called Volatility. Volatility analyzes memory images. And here's an example of Volatility analyzing a Windows memory dump and looking for IP connections. Here is a whole host of recovered IP connections that have significant forensic value. We'd like to know as much as we can about all of these different IP addresses, including their IP geolocation. So if we think about solutions to the IP geolocation problem, which is an old problem, although it's still unsolved, we can imagine different ways of just simply trying to publish location. The way that much content is published today is in the DNS. So for instance, you'll recall that the DNS contains A records, it contains pointer records, it contains MX records that indicate the mail exchanger and the mail server that's used for different domains. And in fact, way back in 1996, RFC 1876 proposed using exactly this kind of a mechanism to publish latitude and longitude for every IP in the DNS. This RFC standardizes what's called a lock or location record. As an example, the UK publishes postal codes this way. If I use dig and I ask for the lock or location record of SW1A2AA, I actually get back a latitude and a longitude. So this seems great, but what's the problem with a technique like this? Well, it turns out that almost no IP addresses actually have lock records. It requires the DNS authority for a particular IP address or a particular domain to actually keep these location records up to date, and that's a significant problem, especially for devices that are mobile. Further, it may compromise user privacy or different kinds of user agreements. So, even though this RFC has been around for a very long time, in practice, it's hardly used at all. The IETF, which is the Internet Engineering Task Force, however, has been very active in recent years in looking at technical means to support emergency and 911 type services over the public internet. This is especially important because things like the traditional phone network, the traditional analog networks, and the PSTN are slowly going away. Today, the particular call center that handles an emergency 911 call is based on the caller's location. It's extremely critical to get this location correct because it's often a matter of life and death. If someone calls 911, it's important to get an ambulance to their house or their physical location as quickly as possible. So if there's any confusion or ambiguity about the user's location, this can actually result in real problems. So in a world where the PSTN goes away and everything is VoIP or voice over IP, how will it work? How will the 911 emergency call center know the location of a user who's on a VoIP phone? providing this kind of information while still maintaining consumer privacy is actually under the purview of RFC 6280, or an architecture for location and location privacy. So the IETF and other companies are working hard on this problem, but it's still very much a work in progress. What other databases of published information about location are available? Well, we know that IP addresses are allocated hierarchically, and these addresses are given to the RIRs, or the regional internet registries. These RIRs get big chunks of address space blocks, and then they sub-allocate to different organizations, such that these big blocks are typically contiguous. We know that these RIRs exist in different physical regions. So for instance, in the Americas, we have ARIN, in Europe, we have RIPE, and in Asia, we have APNIC. So it is possible to use Whois. Whois is a Unix-based command line program to query the databases of these RIRs. Here, I've provided an example where I'm querying APNIC, or the Asia Pacific Network Information Center. And I'm asking APNIC, please tell me who owns this address 1.2.2.3. What I get back is actually information that's quite useful. I see that 1.2.2.3 belongs to a /24 that's been assigned to something called KNet technology, misspelled, in Beijing. But it's important to note that this location that's provided here is the location of the ISP and may be completely different than the host. In fact, the host could be anywhere in China, or it could be anywhere in the world for that matter. So the point here is that Whois can provide important contextual information to the likely location of a particular host, but it's certainly not conclusive. Some ISPs have extremely large IP address blocks. For instance, Comcast may have very large IP address blocks, but a Comcast user could be anywhere in the United States. Of course, there are still yet other databases. The DNS has other records besides LOCK that are used frequently. The DNS pointer record is one that may give us lots of interesting information. If you'll recall, when we talk about the DNS, DNS has A records. These are address records. And an address record maps a name to an IP address. Going the other way, when we look up the name that corresponds to an IP address, these are pointer records. So we may query the DNS and we can say, hey, DNS, who owns this particular IP address? Please tell me the corresponding name for this IP address. What are the problems with this type of approach? Well, first of all, many IPs don't have pointer records. Their ISP or the authoritative DNS simply doesn't maintain pointer records for all IP addresses. If there is a pointer record, they're often incorrect or outdated. And finally, the name that's returned could be really anything. There's no standard scheme to infer location from the DNS name. However, there is often useful location information. I'm going to run through 5 quick examples here just to show you the diversity of the types of pointer records that are out there and the differences between them, the fact that they're completely non-standard, and the fact that some give location information, some don't, and the granularity changes. So let's look at this first one. IAD 23S06 in F8 1E1 100.net. At first blush, this may not look like it contains any information corresponding to the location. However, the astute observer will note that IAD is one of the United States airport codes. IAD in particular is the Dulles Airport in Dulles, Virginia, where there are many ISPs and many very large data centers. So in fact, this is a good hint, although not conclusive, that this IP address and this name that corresponds to this IP address is in Dulles, Virginia. Here is a Comcast address where we see SFBA in the middle. This SFBA is a likely hint that this might correspond to the San Francisco Bay Area. But we note that this is a non-standard abbreviation. This is just something that Comcast came up with. Here's an example from sbcglobal.net. Here we see MILWWI. What could this correspond to? Well, likely this corresponds to Milwaukee, Wisconsin. So we've seen 3 different examples of ways of encoding information about the location, but they're all different depending on the ISP, and they don't follow any sort of standard. Here's an example from a different name. Here, there's really no location information beyond the fact that it's likely in South Africa, although again, this is non-conclusive. Finally, if we have a name such as diamond.nps.edu, here we have no location information. For all we know, diamond.nps.edu could be hosted in Atlanta. It could be the NPS web server, and we're simply using a shared hosting company. So, given all of these problems with databases that contain IP geolocation information, we're left in a world where none of these databases give us any kind of conclusive data on where the host actually is. As a result, there's a whole class of IP geolocation techniques that are based on latency. We'll call these latency-based geolocation techniques. The intuition here is fairly straightforward. When we talk about network propagation delay, we know that network propagation delay is a component of latency, and the propagation delay is a function of the speed of light in the physical media and the length of the physical path. So for instance, the amount of time it takes for a bit to get from my house in Monterey to a host at NPS is going to be much smaller than the amount of network propagation delay to get from my house in Monterey to a host in Boston. If we know the location of a particular host X, the propagation delay between X and the target, or something we're trying to geolocate, is going to be a function of the distance between X and the target. So what that means is that if I'm a host in Monterey and I know my location, if I can measure the latency to another host, that latency is going to be a function of the distance from me to that host. We're going to use that fact in our latency-based geolocation, and I'll show a picture of this in a minute. Next, we can use several hosts with known location, and this will allow us to triangulate the location of the unknown target host. For those of you who have seen different kinds of triangulation, for instance, in wireless networks, the idea is going to be very similar. When we use several different hosts with known locations and do this triangulation, what it does is it adds constraints on where the host could possibly be. So we'll often talk about this kind of latency-based geolocation as constraint-based geolocation. In the literature, you'll sometimes see this referred to as CBG. So let's talk about getting from delay to distance. So the propagation speed of bits in a wire, such as a piece of fiber, can be approximated as, generally we'll say, 2/3 c, where c is the speed of light. We can therefore estimate the propagation delay as a function of distance d. So if d is the distance in meters, the one-way delay is going to be 3d over 2c seconds, where c, again, is the speed of light, or 3 × 10⁸ meters per second. Therefore, given a particular propagation delay, we can lower bound the distance from a monitoring point to the thing that we have a delay towards. It's interesting to think about why this will be a lower bound, and I'll let the astute listener think about that some more. How to determine the propagation delay, though? Going back to our Intro to Networking class, we'll remember and recall that there are 4 sources of network delay. So anytime we talk about delay, we're talking about the sum of the transmission delay, sometimes this is called the serialization delay, the propagation delay, the processing delay, and the queuing delay. Of these four, only queuing delay is variable. The rest of these are fixed. So the transmission speed is fixed, the propagation speed is fixed, and the processing delay we'll generally assume is fixed. So to get a delay measurement, we can do something as simple as sending a ping. So if I'm at my house in Monterey and I ping a target over in Boston, I'm going to get back an RTT, or a round trip time. This round trip time, again, is going to be the sum of these four sources of network delay on the forward and the reverse path. So this is a lot of different network delays, all summed up in a single RTT. So the RTT is the thing we get. How can we pull out the propagation delay? Let's take a moment just to refresh ourselves of these different elements of delay. So here, assume we have on the left a source and on the right a destination. The source is going to be sending some packet, such as a ping, and this is a standard timing diagram where time proceeds going down in the direction of the arrow. So initially, there's a packet that's sent. At the top, this is the first bit of the packet. And then on the right here, we see the time at which the first bit arrives at the destination. Finally, the source finishes transmitting. This is the amount of time from the first bit sent to the last bit sent is the transmission delay. That last bit gets sent and then must propagate from the source to the destination. So sometime later, the last bit of that packet arrives at the destination. If we look at the time between the first bit being sent and the last bit being sent, this is a function of the transmission delay, or the serialization delay. It's how long it takes to clock this out onto the physical media. For instance, it'll take longer if it's a 10 megabit Ethernet as compared to, say, a gigabit Ethernet. If we have a faster link, the transmission delay decreases, and I've shown that in this picture. Next, if we talk about propagation delay, the propagation delay is a function of how far apart the source and the destination are. So here, I've labeled the distance d. The time of propagation delay is the time from when the first bit gets sent to when the first bit actually arrives. So, if my two hosts are actually closer together, the propagation delay will in fact decrease. Conversely, if the hosts are further apart, the propagation delay will increase. So how can we obtain propagation delay? To estimate the propagation delay, first what we'll do is we'll assume symmetric forward and reverse paths. So when we get one of these RTTs, we'll divide it in half. What kind of probes are we going to send? Well, I already said that we would send pings, but what size ping might we send? What we want to do is we want to send as small of a packet as possible. And the reason for this is we want to minimize the component of delay that's attributable to transmission delay. When we send small packets, these can be sent very quickly. Further, we're generally going to assume that the transmission delay is going to be negligible as compared to the propagation delay. It's interesting to ask if this is an accurate assumption. When we're talking about IP geolocation and we're talking about cross-country type distances, it may be the case that, for instance, going cross-country, we're talking about milliseconds of delay, whereas the transmission delay is microseconds or even less. Therefore, the assumption will hold. However, if we're in a data center and we're talking about the difference between transmission delay and propagation delay, within a data center, the propagation delay, where two hosts may be connected by a wire across the room, and there's only 100 meters between the two hosts, then transmission and propagation delay may be very similar. However, in our context, we're going to be assuming that the transmission delay is very small relative to propagation delay, and so it can be ignored. especially since we're sending small packets. But then there's that fourth component of variable delay, queuing delay. How can we account for queuing delay? Well, the answer is it's hard to do that in any sort of explicit manner. But what we can do is we can send multiple probes. So what I might do is I might send 10 pings to a particular host. Now, which of those pings am I going to take? Well, I'm going to take the one that has the smallest delay, because the one that has the smallest delay is the one that encountered the least amount of queuing. Since we don't care about queuing when we're estimating IP geolocation, because all we want to know is the propagation delay so that we can get a distance, we'll always want to take the delay that's smallest, because this will have the least amount of queuing as possible. So therefore, given an estimate of the propagation delay, we'd like to compute the distance d from our pinging source. How accurate are these delay-based distance estimations? Well, there's at least three sources of error. We can have circuitous routing. Paths are often known to violate the triangle inequality, and there can be last mile effects. For instance, things like DSL and cable often add considerable queuing and transmission delay. So these errors can be significant. Let me quickly show you an example of different kinds of latency limitations. These slides are from Brian Erickson in his PAM 2010 talk. So most internet paths are not line of sight to the destination. If, for example, we're trying to estimate the latency between a host in Madison, Wisconsin to Los Angeles, California, we can think about that distance in terms of how the crow flies, or a direct arrow. But paths, as we said, on the internet are actually much more circuitous. In fact, when Brian Erickson and his team measured the latency and mapped it out, the first hop from Madison, Wisconsin en route to Los Angeles, California went to Chicago, Illinois. From Chicago, it went to Pittsburgh, Pennsylvania. From Pittsburgh, it went to Nashville, Tennessee, and then from Nashville, it took a hop over to Los Angeles, California. So this is quite common, that the path that a packet takes is not line of sight, or as the crow flies, but in fact is a much longer path, simply because of the way the links in the internet physically traverse. So keep this in mind when we talk about the accuracy of delay-based distance. Once we have a distance, how can we move from obtaining this distance estimation to an actual physical location, the thing that we're trying to do? Using some terminology you'll see in the literature and in future lectures, we'll define the landmark as the host that has known location that's performing active measurements or sending probes. In particular, this landmark is going to send pings to a target. The target is the host that we're trying to geolocate. The target is the thing that has an unknown location, and we're trying to figure out the target IP's actual location. So the landmark sends pings to the target in order to obtain D. Once we obtain D using the method of taking an estimate of the propagation delay and converting it into an actual distance, it's important to note that this does not tell us where the host actually is. If we have the landmark with known location, the target could be at any point on the circle circumscribed by radius d. Here on the left, I've shown a picture where from the landmark, the actual target could be anywhere on that blue circle. For instance, the landmark could be in exactly the opposite direction. How can we therefore figure out where the actual target resides? Well, the answer here is we're going to use this idea of CBG, or constraint-based geolocation. So instead of sending these active probes, these active pings from a single landmark to the target, we'll use multiple landmarks where each of these landmarks has a known location. And what this will give us is a whole bunch of these different circles. Each of these circles defines the possible region of the target from that particular landmark. When we take the intersection of all of these possible regions, this gives us the actual feasible region of the target. Here I've shown an example where you can see many of these different circles, all corresponding to the distance estimation from different landmarks to the target. And the intersection of these is actually this polygon that is in orange here. So the target must be somewhere in that physical region. I've mentioned previously that CBG has been shown to have significant error. Referring back to Brian Erickson's work in 2010, his group found that CBG has an average of 322 miles of error. And even more importantly, or perhaps as importantly, this error plot has a very long tail. This CDF on the right is taken from Brian's 2010 paper, where we can see the cumulative probability over all of their geolocation estimates for constraint-based in the red line. And in the red line here, we can see that the median is almost 500 miles of error, and this tail goes off all the way to 2,000 miles of error. So some of these estimates are way, way, way off. The bottom line is, basic CBG type techniques work well when we're talking about coarse-grained inference, when we're trying to do geolocation at the country level. In the next lecture, we'll look at some more advanced techniques that have lower error and can provide fine-grained geolocation. Finally, I'd like to mention that there are many commercial solutions out there for doing IP geolocation. These are almost all motivated by a need to find the IP geolocation of end hosts for those exact reasons we've mentioned before, for doing different kinds of advertising, authentication, security, and so on. As a result, IP geolocation work has focused almost exclusively on end hosts. So when we try to geolocate infrastructure, things like routers or servers, the geolocation has even worse error. We don't know actually how these commercial solutions work. The reason being is that the underlying algorithms and methodologies are closed and proprietary. However, it's almost assured that they all rely on a combination of techniques, including things like the database lookups that we've discussed previously from multiple different databases like Whois and the DNS, and using CBG, and doing manual inference. A few examples of these that you may wish to look at or use in your own research are MaxMind, Digital Envoy, Host IP, IP Elegance, Scyscape, and Edgescape. There's an actual paper from 2011 that compared all of these. This paper from CADA was called a geolocation bake-off and showed that some of them disagree fairly significantly for the same IP address. In your own work, you may wish to use MaxMind. I mentioned MaxMind because they do provide a free coarse-grained geolocation database that has APIs for Python and all of the popular different programming languages. This is useful when you only need a fairly reasonable estimate of IP geolocation and not a high precision estimate. So take a look at these, and in the next lecture we'll cover fine-grained IP geolocation. Thanks!